So in this video I want to show you how to analyze your Excel data, and in this spreadsheet in front of you what we have is we have the standard curve measurements up here, and then we have the measurements for the first unknown dye over here. This is 1000 microliters and 500 microliters of that first unknown, and we also have the measurements for the second unknown here in terms of microliters of the dye, and also the absorbances down here as well. And I want to show you how to convert this into something like this, where we have a standard curve there and we have different ways of calculating our original concentrations of our unknown dyes using the standard curve and also using the extinction coefficient. Okay, so going back to our graph over here, let's do a bit of formatting first. Let's bold a few things, and bold is just Control and then B on the keyboard if you're on a PC, or if you just want to select the cell you want to bold and come up here to the B button and click that. So let's bold these ones. And because our data for our standard curve covers this entire range of cells, let's get Excel to merge and center this title in the center of these 7 or so cells. To do that, come up here to the merge and center button, you click on that, and then Excel will merge all those cells together and put that first cell in the center. We can do the same for the unknown one, which is over here. So highlight those 2 cells with the mouse and then click merge and center, and again with unknown number 2 as well. Okay, something else that you may want to try out is actually how to get this micro symbol over here. So the micro symbol is, you can either use just the letter U on the keyboard, that's quite easy, or the other way to actually enter that micro symbol is by holding down Alt on your keyboard, followed by on your number pad the numbers 0, 1, 8, 1, and then release the Alt key on your keyboard, and that will enter for you the micro symbol. So again, it's just basically holding down the Alt key and then pressing 0 followed by 1 followed by 8 followed by 1 on the numeric keypad, and then releasing the Alt key. Okay, so the first piece of information that we need in order to work out our concentrations of dye inside our cuvette in order to construct our standard curve is actually the original concentration of dye in this stock. Okay, so for this particular dye, let's type here the stock dye concentration. Remember, always put units down. It was quoted in millimolar. For this particular dye, it was actually 0.078 millimolar. Okay, now what this means, what this concentration means, okay, the stock dye's concentration 0.078 millimolar, which expands out to 0.078 millimoles per liter, which is also the same as 0.78 micromoles per milliliter. And let's express this left part in a quite nice number, which is going to be 78 nanomoles per milliliter, also known as, well actually no, let's leave it at that, 78 nanomoles per milliliter. This means that from our stock dye, okay, from our stock dye which is sitting in a big bottle, okay, if we took out 1 milliliter of our stock dye, then we would have had in that 1 milliliter, there would be 78 nanomoles of this particular dye floating around inside that 1 milliliter. Okay. Also means that if we took out 2 milliliters, okay, there would be 156 nanomoles of the dye floating around in those 2 milliliters. Okay, so say in this particular situation here, we took out 800 microliters of the dye, and 800 microliters of the dye is actually equivalent to 0.8 milliliters of the dye. Okay, so if in 1 milliliter there's 78 nanomoles, then in 0.8 of a milliliter there is 62.4 nanomoles of the dye. Okay, so this 62.4 nanomoles of the dye was sitting in the 0.8 mils, and what we did is we added that to a cuvette. So here's our cuvette, and we had the 0.8 mils coming over here, and that contains 62.4 nanomoles of the dye. Now the rest of this solution, the other 0.2 mils in this instance, okay, came about because of water. water we had 200 microliters, which is equivalent to 0.2 milliliters. And so in this entire 1 mil cuvette, okay, how many nanomoles of dye were there? Well, no nanomoles of dye came from the water, and all the nanomoles of dye must have come from this addition over here, which means that in this 1 mil, there are 62.4 nanomoles of dye. Therefore, we can say that the concentration of dye, okay, is going to be 62.4 nanomoles per mil, and that's the number we would write up here, 62.4. Now the idea is to get Excel to work these calculations out for us, and so let's see what we've done with our numbers. Over here we have the number in K2, okay, this is K2, let's put that in red actually, K2, okay, so that number is 0.078, which is this number over here. Then to that number we times it by 1,000 to get to this number over here, and then we multiplied that number, okay, by the volume added in milliliters. Now what we could do here is, this probably isn't the most straightforward way to do it, but in order to get whatever needs to be in here, okay, this has to be equals to the stock concentration, okay, times by 1,000, and then we had to multiply it by the volume added, okay, and then so we have to times by the volume added, which was, so let's put the volume of dye here, and that was the volume of dye divided by 1,000. Okay, so that again, if we write it out, is stock concentration times 1,000 times the volume of dye divided by 1,000. Now, because we have times 1,000 over here, and we have divided by 1,000 over here, what we can do, let's just strike or cancel both of them off. And so technically what should go into that cell will be the concentration of the stock times by the volume of the dye. Okay, so let's give that a go. The stock times by the volume of the dye. Okay, so let's go over here to cell F4 and start working out our concentration of dye in the cuvette. F4 equals, and remember when you start an Excel formula or want Excel to work something out for you, always start the cell off with equals. That tells Excel work something out mathematically for me. Okay, so it goes equals the concentration of dye, and then times by, and times, remember, is the asterisk character, times by the volume of dye in microliters, and then you press enter. And there we have our 62.4 nanomoles of dye per mil in that particular cuvette. Now, Excel is really great because you can get it to propagate this formula for you, so you don't need to write it again and again in each different cell you want the formula to apply to. So in order to do this, there's a thing called a click and drag. In order to click and drag, hover your cursor over the bottom right hand side of the cell and then click on it and literally drag this formula across. Now what Excel does in this instance is it's able to push the formula and update the cell references to the left and to the right. And sometimes it's quite useful. For example, here, we do want in G4, we do want G4 to refer to 1,000 in the red. But the thing is, we don't want it to move or change the reference to K2, which is the concentration of stock dye. So how do we stop this from happening? Well, going back here to F4, we have the K2 and also the F2 over here. And we know that red we do want to move and blue we do not want to move. And so to force Excel to actually keep K2 constant and not to update that reference, we put a $sign in front of the K and a $sign in front of the 2. And then we press enter. And that is called absolute referencing. And that tells Excel to actually not move or not change K2. So for example, here we see it has not changed K2, but it has updated the red box. Okay, so the next thing to do is actually insert a graph, insert a standard curve. And to do this, the best way to actually insert an XY scatter graph is to insert a blank one. So click somewhere outside of your data range inside your spreadsheet, then come up here to the Insert tab, and then go to this button and insert a scatter graph with dots. Let's move this up here. Okay, so in order to actually tell Excel what data to plot onto the graph, you can right click on the graph and then choose the select data option. Okay, this dialog will open up, allowing you to add a series, which is a set of dots onto your particular graph. So let's come over here and click the add button. And now Excel will ask us for a series of X values, which is your independent variable, which in this case is your concentration of dye. So the X values is equal to these, and again you can click and drag with your mouse and release. And then with the Y values, let's get rid of whatever's there, and the absorbance is our dependent variable, and that's our Y values. So we can click and drag, select these cells over there, and then click OK and OK again. So let's format this chart now. First of all, the chart should normally not have any grid lines because they don't really add any value to the chart. And so click on the grid lines and press delete on the keyboard to get rid of them. Then the chart title, let's call this the dye X standard curve. And remember, your chart not only should have some description like a title, but it should also have axis titles too. So something saying, you know, what this 30, 40, 50 is, or what the 0.4, 0.6, 0.8 is. To insert these axis titles, you click onto your chart, okay, and then click the plus button, and then you want to select axis titles. Now to change them, all you need to do is click on them and then type something in. So let's, for example, say concentration. A better way to do this, for example, however, is to actually get Excel to refer to an existing piece of text on your spreadsheet. So for example, what we want to actually put as the axis title on the x-axis already exists over here in A4. So what we can do is we can get Excel to actually refer to A4 when it pulls out or when it draws the graph. Okay, so do that, click onto your axis title and then press the equals button. And again, equals just tells Excel do something for me. Okay, so it'll be equals to A4. And you can see Excel selected this for you, and once you press enter, the contents of cell A4 will actually land as part of your x-axis title. We can do the same for the y-axis. So here we have axis title equals the absorbance, click into A5, press enter, and that's your absorbance title right there. Now the benefit of doing this is because later on, if you've changed your mind and you want to express this in terms of microliters per liter, micromoles per liter or something, you change some of these values around, then your x and y axis labels will automatically update, just as the data updates in the graph as well. Okay, so the next thing for the standard curve is to actually insert a line of best fit, also known as a trend line. To do that, right click onto your dots and then go to the add trend line option. This will add that line of best fit, and in this case it's a linear line of best fit, which is great for us. We also want to come down here and display the equation and also the r squared. Now the equation of the line is a mathematical description of the gradient and also the intercept of this line. And so here you see y equals the gradient times x plus the intercept. You also have the r squared here, and the thing about the r squared is that it's important to note that the r squared only represents how nicely or how closely that line of best fit fits your data points. It doesn't actually tell you how accurate your data is. It just says that that line that Excel has drawn on, the closer it is to 1, the closer the r squared is to 1, the better that line fits to your data points. Okay, so the thing about this trend line is that its values, its y and x values actually correspond to the particular values on the y and x axes of this particular chart. And so you see the y value over here, that corresponds to the absorbance, okay? And the x value over here corresponds to the concentration of the dye. So really what this equation is telling you is y equals, okay, so y is absorbance, so it's telling you A equals particular constant, okay, so the constant, and x, which is the concentration. Well, let's call this a different thing. Let's call this, let's just put in a filler constant over there, epsilon, okay? And for this x, it is the concentration, which is abbreviated as C. And so what you see here is that it's basically the beginnings of the Beer-Lambert law. You have A equals EC, and this E, the epsilon, is a constant, which is, in this case, 0.0133. Now, the extinction coefficient of this particular dye, the extinction coefficient that we've been given for this particular example dye is actually 12.5 per millimolar per centimeter. Okay, So the question is, well, for this particular dye, epsilon is equal to 12.5 per millimolar per centimeter. Now, why is that different to the epsilon that we're getting from this standard curve equation? Well, they're not actually that dissimilar after all, because if we look at the standard curve here, the units of the x-axis is in nanomoles per milliliter. Okay, so the extinction coefficient that we're getting from our standard curve is 0.0133, and because the x units, okay, the concentration units are in nanomoles per milliliter, which is equivalent to micromoles per liter, which is equivalent to micromolar, this means that the units for our extinction coefficient from the standard curve is actually in micromolar, or in per micromolar per centimeter. Now the question might be, well, how do we convert between these? Okay, and the way is to actually ask about these extinction coefficients in English. So an extinction coefficient, when it's expressed in per millimolar per centimeter, means that a 1 millimolar solution, okay, will give an absorbance of 12.5 in a 1 centimeter cuvette. What this extinction coefficient is telling us is that a 1 micromolar solution will give an absorbance of 0.0133 in a 1 centimeter cuvette. And this makes perfect sense, because a 1 millimolar solution is about 1,000 times, well, it is 1,000 times more concentrated than a 1 micromolar solution. Okay, so this guy is more concentrated by about 1,000 times. Okay, so if the 1 millimolar solution is 1,000 times more concentrated than the 1 micromolar solution, then you'd expect that the absorbance given by the 1 millimolar solution is about 1,000 times greater than the absorbance given by the 1 micromolar solution, and that's what we're getting here. Okay, we're within a bit of error. So essentially what we're saying here is that if we express this extinction coefficient, or this extinction coefficient, in millimolar units, it will essentially be 13.3 per millimolar per centimeter, which is pretty close to the quoted extinction coefficient of 12.5. So the whole point of working out the standard curve is actually to be able to apply it to work out the concentration of these unknown solutions. Now the standard curve tells us a relationship between the absorbance and also the concentration in the cuvette. Okay, so this is the concentration of dye on the x and the absorbance on the y. So if its absorbance equals constant times concentration plus another constant, what we can do is we can rearrange this equation and then essentially solve for x. And so what we have is we have now x is equal to y minus 0.0006 divided by 0.0133. Okay. And so this, if we are able to find out the absorbance of a solution, then we can easily find out the concentration of that solution as it's sitting inside that cuvette. So, for example, over here, in one of the cuvettes, we've added 500 microliters of the dye. Okay, so let's draw it up here. In this cuvette, we have 500 microliters of the dye, and the other 500 is obviously water, and that has given us an absorbance of 0.417. Okay, so this means that y, which is the absorbance, 0.417, subtract the intercept, divide by the gradient, and what we get is we get 31.31. Now the question is, what kind of units are these? Well, the units come from the graph because the x comes from the graph, and so the graph units on the x is nanomoles per mil, and so therefore this will also be nanomoles per milliliter. Okay, so the question now is, well, in this cuvette, what's happening is that you've got 500 microliters of the dye, but you also had another 500 microliters, and that was water. And so the entire volume of this cuvette, or the solution in the cuvette, was 1 milliliter. What this is actually describing here is that in 1 milliliter of the cuvette, there were 31.3 nanomoles. Okay, so in this 1 milliliter of this cuvette, after the dye and the water were added, there were 31.31 nanomoles of the dye floating around. Now, if we ask ourselves the question, well, where did these 31.31 nanomoles come from? Well, they sure didn't come from the water, okay? And they only came from the dye. So then, these 31.31 nanomoles of the dye came from this volume of dye here, which is 500 microliters of the stock. Okay, and this expression 31.31 nanomoles of the dye per or in 500 microliters of the stock, this is actually the concentration of unknown number 1, or an expression of the concentration of number 1. So let's solve this out. 31.31. So if we do the division, if we do the division, this turns out to be 0.06262 nanomoles per microliter. Then if we multiply both sides by 1,000, what we'll get is 62.62 nanomoles per 1,000 microliters, and this is just 62.62 nanomoles per milliliter. And now this expression of milliliters is actually the expression of in the original unknown stock. Okay, no longer is it 1 milliliter in a cuvette, it's 1 milliliter of stock. This means that if we take out 1 milliliter of the stock, in this 1 milliliter should be about 62.62 nanomoles of the dye. So let's think about how to get Excel to work this out for us. What we have information-wise is we have the microliters of the dye, okay, sitting in cell C10. We have the absorbance sitting in cell C11. We have the absorbance being plugged into the equation of the standard curve over here. Okay, so we have the absorbance minus the intercept divided by the gradient. Okay, so we'll need in our Excel spreadsheet somewhere where there's a representation of the intercept and also the representation of the gradient. And so let's put it here, so let's say put our gradient over here and put our intercept over there. Okay, so C7, for example, can be our gradient and E7 can be our intercept as an example, maybe F7. Now, the number that we can put in here, let's put in the concentration of dye in the cuvette. Okay, let's put in this initial calculation, okay, over here into A12. So this initial calculation will be equivalent to, or the value that sits in there, okay, will be equal to the absorbance, which is in C11, minus the intercept, okay, which is going to be, let's say it's in F7, okay, and it will be divided by the gradient, which we'll say we'll put into C7 over there, okay, and that will give us the number of nanomoles, or this is the nanomoles per mil in the cuvette. Okay, and the next calculation we did was then where we took into consideration how much volume of dye was actually added to give this number of nanomoles. Okay, and the number of the volume was 500 microliters. Okay, so what we did is we took the value, which is 31.31, and we divided by 500, which gave us this value here, and then we times that by 1,000 to give us an expression which was in these units. Okay, so here what we can do is we can say the original concentration, okay, which still gets reported in nanomoles per milliliter. So this one down here would be equal to, well, it'll be 31.1, which would be the value in C12. So this would be equal to C12, and then we would have to divide by the volume, okay, which is in C10. and then we would have times that by 1,000 to bring it up to this particular value here. So it would be, oops, times by 1,000, and we'd hit enter, and that's the kind of value or the formula that we would get there. Okay, so let's try that in Excel. Let's type down, this can be the concentration of di X, okay, in the cuvette. And remember we had the units of nanomoles per milliliter. Let's just bring this out, stretch it out so we can see the entire heading. And over here, remember the concentration of di in the cuvette is equivalent to this, well, is based on this standard curve over here. So remember it was a rearrangement of the standard curve. And before we could be able to do that, remember we had to put the gradient and also the intercept in these particular cells. And so here the gradient is 0.0133 and the intercept is 0.0006. So let's label these up. Input gradient is equal to that, and this is the intercept is equal to that as well. Now, if you know how to use the slope and the intercept functions in Excel, feel free to use those functions at this point. If you don't, then we'll teach you about those functions later on in another component of Excel. Okay, so now we have our gradient and intercept on the actual spreadsheet itself. Let's come over here and start a formula up. Remember, it was y equals mx plus b, and if we rearranged it, it would be x equals y minus b on m. Okay, so equals y minus b, y is the absorbance, minus b, which is the intercept, okay, on m, which is the gradient. And we'll press enter, and we have our 31.31 nanomoles per milliliter here. Again, we can drag it left and right, but before we drag, what we should do is we should tell Excel to fix certain cells. We should tell Excel, before we drag, we should tell Excel to fix certain cells, and these cells are going to be the gradient purple cell and also the intercept red cell. Okay, so coming over here, we can again put dollar signs in front of the letter and the number of the ones we want to fix. Okay, and then press enter, and now we can drag left and right perfectly well. Okay, and the next step, if you recall, is actually to work out the original concentration. Okay, so let's say this is the concentration di X original. Okay, and remember that was also in nanomoles per milliliter. And that was equivalent to, or equal to, the concentration in the cuvette divided by the volume of di, and then we times by 1,000 to get this value out here. And again, we'll drag left and right. And this time there's no need to fix any values because the values need to be updated. Okay. And the last thing to do here, I guess, is to work out the actual average. The point of doing 500 and 1,000 over here is actually get some replicates going. And also all science is based on replicates. And so let's put the average concentration of di X in original. And this again can be nanomoles per milliliter. Again, we'll expand that out, and let's find out, well, let's combine these two cells first by using the merge and center function, and then let's put in this cell equals the average, okay, A-V-E-R-A-G-E, of these two cells. You can click and drag those two cells, close the bracket, and press enter, and that's your average concentration that you figured out for the original unknown one stock. Now, the beauty of Excel is that if you set your data up in a particular way, you're able to propagate your formulas across. And so because I've set my data up in this particular way, when I have a think about what's happening in my unknown 2s, okay, so in my unknown 2, I have still a cuvette, okay, and I've added, for example, 50 microliters of my very, very, very concentrated unknown 2. The other 950 is water. Okay, just like over here, okay, well rather over here, I had a situation where it was 500 microliters of the dye and 500 of the water. Over here, I've got 50 of the dye and 950 of the water. Now the calculations that apply to unknown 2 are exactly the same calculations as apply to unknown 1. And because I've set my data up in this particular way, what I can get Excel to do is literally to copy the formulas or propagate the formulas over by click and drag. So I select those two, drag this all the way over, and all the calculations are done for me already. Isn't that fantastic? Again, we need to work out the average, so let's highlight these 3 cells, do merge and center, and this can be equals to the average now of these 3 replicates. Okay, so in this instance, what we've done is we've worked out the concentration of dye using our standard curve. So let's write using standard curve over here and put that in bold. Now another way to actually work this out is by using the quoted extinction coefficient. So let's put another heading down here saying using extinction coefficient. Okay, and let's just copy these data down here because we'll be using the same data again. We'll copy these data headers as well. Okay, now the quoted extinction coefficient for this particular dye, let's put over here. So the extinction coefficient, which is quoted in per millimolar per centimeter, is actually 12.5, okay, for this particular dye. Now, if you want to format this and make it a little bit prettier, you can actually put superscript on this. In order to do it, click into the cell and then come up here to the formula bar, select the text you want to turn into superscript, come over here to the font dialog, and what you can do is you can highlight or click superscript, and when you press OK, it won't look very impressive over here, but if you look over here, it would actually be superscripted. Okay, we can do the same for the per centimeters as well. Okay, and then we'll press enter to confirm. And there's our extinction coefficient sitting in cell L4. So using the extinction coefficient, we can also work out the concentration of the dye. Okay, so the extinction coefficient says, or the extinction coefficient is 12.5, and that's 12.5 per millimolar per centimeter, and we have A equals ECL. Remember, L is 1 centimeter, okay, E is the extinction coefficient, concentration is what we want to work out, absorbance is what we know. Okay, so we know these absorbances. Therefore, we can say the concentration is equal to absorbance on extinction coefficient divided by the path length of the cuvette. Okay, so going back to this example here, 0.417, okay, divided by the extinction coefficient, which is 12.5 per millimolar per centimeter, times by 1 centimeter, which is the path length of the cuvette. Okay, and this turns out to be 0.03336. The question is, well, what units are these? Well, centimeters here will cancel out. The millimolar doesn't cancel out, but this -1 will turn it into a numerator unit, and so therefore we have millimolar here. Okay, so 0.03336 millimolar is millimoles per liter, is equal to 0.03336 micromoles per milliliter. Let's make this pretty. This would be equal to 33.36 nanomoles per milliliter. Okay, so again, what this is telling us is that in this cuvette, okay, in this cuvette we're measuring this absorbance, which is 0.417, and this absorbance is telling us that the concentration of dye in the cuvette is 33.36 nanomoles per milliliter. All right, so in this cuvette, it was half dye, half water, and in the entire cuvette, it was 33.36 nanomoles per 1 milliliter in there. Okay, so therefore here we can again add, we have the dye in the cuvette, and let's keep it at these units to make it match to the units before. We have nanomoles per milliliter, and this guy over here would be equal to, well, it would be equal to C19 divided by extinction coefficient, which is sitting up here in L4. Okay, and then we multiplied that by 1,000 to get to this nice number over here. And so that would be the formula we put in to cell C20. And then the rest of it is very similar to what we did up here. So we need to account in this next row, okay, in this next row here, which is similar to this row up here, account for the volume of dye, and then find out the average, and then we're done for that calculation. So let's do that in Excel now. Okay, so this one, let's just copy over this. Concentration of dye in the cuvette. This was equal to the absorbance divided by the extinction coefficient, okay, times 1,000. And again, we want your L4 to be fixed, and so we'll put dollar signs in front of the L and in front of the 4 that we can drag left and right. And then we can work out the concentration of dye in the original, okay? And just like we did over here, we did the concentration of dye in the cuvette divided by the dye volume in microliters times 100. We can do the same here, equals the concentration divided by the dye volume times 1,000. And again, we can click and we can drag. And again, we can work out the average. Okay. Now, instead of copying or instead of retyping this, what we can do is we can actually get Excel to just copy these down for us. So let's highlight these two cells, press Control C or copy on the keyboard, and then come down to this cell here and press Control V, which is paste. And what Excel has now figured out is we want to actually copy the formula and update those references. So if we click into this particular row cell here and come up here, you can see Excel has automatically said, well, let's calculate the average now of these two numbers instead of those two numbers. Okay, so Excel, if you know how to use it, it's a really powerful, fantastic tool to really ease your calculations.